speak on the stochastic Allen-Cahn and Cahn-Hilliard equations. And please welcome.
Okay, thank you. First of all, of course, I would like to thank the organizers to give me an opportunity to come back to this very pleasant institute and remind me about the stay I had there 2 years ago. So, as Stoch mentioned, the work I'm going to talk about is jointly written with Dimitra Antonopoulou and Georgia Karali from Heraklion, and it's on the stochastic Cahn-Hilliard and Allen-Cahn equation. So this is my talk will be divided in several parts. The first part will be devoted to introduce the model. That means describes this PDE and the way we are going to perturb it by some stochastic term. Then we'll state a result about well-posedness in LQ, namely starting with an LQ of some domain O initial condition, get existence and uniqueness of the solution taking value in the same space. And then we'll discuss imposing more regularity, more conditions on the domain and on the coefficients, some regularity of the solutions, of the trajectories of the solution, and eventually go to regularity of the distribution, namely existence of a density. So this PDE is stated on a, I guess this is a pointer, on some rectangular domain, and for part of my talks it will have to be restricted to this rectangular domain in dimension 1 up to 3. And always in the beginning, we can afford to deal with a bounded piecewise smooth domain, so that's slightly more general one. So my notation will denote by new outward normal. How strictly positive is what physicists call a diffusion coefficient. Of course, it has nothing to do with what probabilists would call a diffusion coefficient for an SDE. And the main feature of this equation is twofold. On one hand, there is a polynomial nonlinearity of degree 2 with positive leading coefficient. This turns out to be very important. The sign of the positive leading coefficient is absolutely fundamental. And you can think of it as, for example, the derivative of a double equal potential. And the second main feature of this equation is this operator. That means we have minus, well, very soon I'm going to normalize rho to be equal to 1. But what is very important is that I do not have here, as usual, the Laplace operator, but the square of the Laplace operator with a minus sign in front of it. So that's kind of the main part, so that you have this very smoothing operator, by the way, because minus, if you had here the Laplace operator, it's going to be smoothing, but if you square it, it's even more smoothing. And then with these two minus signs, you encounter this nonlinearity with polynomial growth, but with a Laplace operator in front of it. So if you just forget about this second bracket, this is a so-called Cahn-Hilliard equation. And if you add the second bracket, it's very similar, except you have lost this Laplace operator with a minus sign in front of it. You have the Allen-Cahn equation, plus some perturbation, which in my talk is going to be driven by space-time white noise. So the reason why we can afford going up to dimension 3 is exactly what I mentioned, namely that this B Laplace operator is much more smoothing. All right, we have some initial condition which was imposed in the open set, and some kind of homogeneous, because it's 0, Neumann condition. But because of the fact that this operator is a fourth order operator, it's twofold. On one hand, we have that the derivative with respect to the outward normal is 0, but also the same condition has to be imposed of this same derivative for the Laplace operator on the boundary. Okay, so of course this equation has been studied a lot by analysts for deterministic forcing, this kind of deterministic forcing with this third order polynomial in many situations by lots of people. And maybe I should have mentioned that my two co-authors are analysts. They are PD persons, and I'm the probabilist in the team. So let me try to give you, but I am not specialist of these physical issues, some understanding of what this equation models. So the in this Cahn-Hilliard equation, it models some concentration of alloy with some phase separation. So So the Neumann boundary condition are going to model conservation of mass and insulation. And this double equal well potential I mentioned is some kind of free energy. Now, the general equation is going to model what's called diffusion absorption phenomenon, and also desorption and absorption dynamics. But don't ask me too many questions on this issue, because as I tried to mention, I'm no specialist of that, to be honest. So also these models appear in statistical mechanics, namely that the corresponding PDE can be obtained as a limiting PDE when some particle system is being observed, but by some rescaling. So this is a kind of mean field mathematical model which comes from statistical mechanics, which gives a motivation to be interested in such a PDE. All right, so now that you have some flavor, I hope, about what the interest of this equation of these PDEs as physical purposes are concerned, let me move to now stochastic forcing. All right, so now I'm adding to this equation. Here, just look at the Cahn-Hilliard equation. That means that I've just removed the second part I mentioned a moment ago. And now I have a forcing. I'm adding to the forcing some diffusion coefficient, some sigma coefficient, some functional of my solution at point x and t, multiplied by some Brownian motion. But of course, it's not Brownian motion. As I mentioned here, I have space-time white noise. So this notation is, of course, completely formal. And now let me mention some results which are already known for such equations in dimension 1. The first paper was written by D'Apreto and Debuche in 1996. So they prove what posedness of this equation in dimension 1 with additive space-time white noise, which is going to be the framework I'm going to deal with, and also in dimension larger than or equal to 2 for additive colored noise. Okay, so that is the very first result, as far as I know, in this random model. Then going from dimension 1 up to 3, again, for this stochastic Cahn-Hilliard equation, there were several papers by Cardon-Weber, one joint paper with Cardon-Weber, where the idea was to go with a space-time white noise and multiplicative white noise in dimension 1 up to 3, taking advantage of the fact that the Bielaplace operator is indeed very smoothing. But the problem is that the diffusion coefficient was Lipschitz. That's no harm, but it was bounded. And the technique was really heavily depending upon the fact that the diffusion coefficient was bounded. And let me also mention some similar result, but with a fairly different nonlinear term here, which is a logarithmic term that's up to some constant, which has to obey some rule. There is some threshold between the true nonlinearity and this nonlinearity for the f term, which is no longer a polynomial of degree 3. And this is done only in dimension 1 on some very specific open set and with reflection measures. And it is a recent paper by Debuche and Goudenèche. All right, so now let me try to mention what I'm going to mean by solution. That's very classical. So that means that I'm going to put all the operators on some very smooth function. So let me suppose that phi is a C4 function on my open set with exactly the same boundary conditions. And so I'm going to introduce a filtration, which is, as usual, generated by my space-time white noise, whatever the position location in the open set is, but provided that S is less than or equal to T. And I'm putting all the derivatives of this smooth function as is completely usual. That means that I'm looking at my solution in a weak sense for analysts. But of course, I'm going to look at my solution as in a strong sense for probabilists, because I'm given a space-time white noise and I'm going to deal with it. All right, so global existence. As I mentioned, the first result is about global existence if I start with an initial condition, which is in LQ, with some Q large enough, and my diffusion coefficient, so to speak, will be globally Lipschitz, fine. But I would like to go beyond the fact that it's bounded, and I have some kind of sublinear growth, namely an upper estimate of absolute value of sigma of u in terms of a constant, 1, plus some power of u, but I cannot go up to alpha is 1, which would be linear growth. I have some weaker assumption. Okay, in that case, the first result we have is that this stochastic Cahn-Hilliard and Allen-Cahn equation, we can add this extra term, which is harmless in a way, because the main part is the fourth order operator. We'll have a unique weak solution, and on top of that, it's going to be bounded almost surely in with respect to time, taking value in that space. Okay, of course, this improves previous results on two hands. On one hand, we can add the Allen-Cahn part, but this is no big deal. But on the other hand, we can go beyond this, affording our diffusion coefficient not to be bounded anymore. So maybe let me describe you vaguely how the proof goes. Well, the first simple-minded idea is kind of standard, because in fact we are following the line that D'Aprato and Giuseppe and Arnaud would use, namely, you have something which has some polynomial growth, you first truncate it and go in kind of more standard framework. But the problem is that you have to raise the bound of the threshold and hope for the best when you increase it and let it go to infinity. And that's why we are going to get almost sure convergence by some kind of limiting effect. And we do not have estimates for the moments. We just have that almost surely it's bounded, but we cannot put our hands on moments. All right, so the first step will be to get an integral representation. So here we are not really going to look at mild solutions, as many people are doing in this audience, but we are going back to the green function, which is more or less the same. So because we want really to focus on that and not be annoyed by the Allen-Cahn part, we are going to introduce an operator, which is minus the square of the Laplace operator plus itself, and looking at the fundamental solution with the given boundary conditions. And in a moment, I'm going to describe you upper bounds that you can get on this green function and its space and time derivatives. Because in fact, this equation can be put in a very general framework where it's a parabolic equation in the sense of Petrovsky, and there are lots of estimates at hand on the green function and its various space and time derivatives, provided that we have some kind of called complementary boundary conditions. And in this framework, everything is fine, so we can enjoy we can take advantage of lots of properties on this green function. So we put all the partial derivatives in front of this green function, and as usual, we can write our solution in this way. Okay, now as I told you, lots of information is at hand to get upper bounds of the green function, some space derivatives of the green function, and let me focus on the Laplace operator on the green function and some time parameters. As you can see, what's going on in the right-hand side, well, it looks as if it were Gaussian, except that the exponents are wrong, right? If you had the heat equation, you would have exactly a Gaussian kernel. And here, it doesn't write, it's similar but different, because here, instead of having 2, as you would expect for a Gaussian kernel, and -1 for the time parameter, you get 4/3 and 1/3. And in front of it, if you want to get a normalization coefficient, of course, well, dimension is going to show up, and you will have the time parameter to the power minus d/4. So that means that there is a ratio of 4 between powers which appear in the space parameter and power which appears in the time parameter. Now, when you start differentiating, well, of course, it's going to deteriorate. Your time coefficient in front is going to be deteriorated, and it's going to be deteriorated by -1/4 each time you take a derivative. So if you have the Laplace operator, you subtract to the previous negative power of t you had, you subtract -1/2, so twice -1/4. That's why I wrote it at it in this foolish way. And if you now take the time derivative, it's even worse, namely that you decay your coefficient in front of your exponential term by -4 times 1/2. All right, and not only that, but you also can get upper bounds. And here I think I forgot to say that you can do that in the case that your domain is a bit more regular than the general one. At least I do not know how to do it in the general one, in the general case. Namely, you can get your hands on increments of your green function between two locations, integrating with respect to the other two parameters, and you get upper bounds in terms of powers of the increment of the difference between these two locations. And you can do the same for time parameters, integrating over the small interval because s is less than t, or for the remaining part. And both exponents are consistent in the second case. And there are some thresholds which depend upon the dimension and which again are different from those you would get for the green function for the heat equation. And they are better in a way because you can go, they are better because your Laplace operator is more smoothing. All right, now I'm going to cut. So I'm going to cut according to the Q norm because I had an initial condition which was living in LQ of O. And therefore, whenever my norm, the norm of my solution is too large, this is done by this cutoff function, which matches 1. It's defined only on non-negative items. It's 1 if x is less than or equal to n, and it's 0 if x is larger than or equal to n minus 1, and it has some kind of nice bounce on the derivatives. So I cut off for the nonlinearity, the polynomial nonlinearity, that's normal. But because also I want that sigma not be bounded, I also cut off in the stochastic interval. So I get another equation, and I hope to be able to use a fixed point theorem. So I have to see what kind of estimates I can have for both deterministic and stochastic intervals. All right, so the kind of fixed point estimate is going to take place in that space of adapted processes, such that uniformly in time, I have some moment, some beta moment, beta being larger than or equal to q, of the q norm with respect to my space variable. And I have to take a close look at the stochastic integral, which this operator is denoted by L. And there is a price to pay that sigma is not bounded anymore, namely using some kind of Kolmogorov criterion. That means looking at increments the way I mentioned a moment ago. I can here have some estimates uniformly with respect to time and space, but my threshold is going to show up in the right-hand side, and alpha was this restriction I had to impose on the growth condition on my diffusion coefficient. And once I've done that, I subtract, and here I'm following exactly the strategy which was used in previous papers on the Cahn-Hilliard equation. I'm subtracting this stochastic integral and introducing a new process which is denoted by Vn. And then I'm kind of going back to a deterministic setting. So I'm going to look at a priori estimates I can use in this setting. So I'm writing down the equation, which now is solved by this difference. And of course, there is no stochastic integral anymore because it's hidden here inside of this truncation formulas, truncation map. And the first step will be applying minus delta plus identity inverse and getting some estimates on the first moment in terms of this guy, which in fact is connected with the eigenvalues of my operator, so of the Laplace operator. So this shows up, but this I can put my hands on. And another second inequality, which is very important, is taking advantage of the fact that f is a third-order degree polynomial. So the sign doesn't show up because it has to be deep in the technique to really see it showing up. But it's a third-order polynomial, and therefore you have some idea on differences, how to upper estimate differences, using Hölder's inequality and working a bit, going from Galerkin approximation and extending it to the whole equation. You can get another estimate of that kind. Okay, so that means that we have two kinds of estimates, and now this is going to be handy because from that we may hope to get an idea of how far we can hope to go with our truncated estimates as the truncation goes to infinity. So let's denote by Tn the first time that the Q norm is larger than or equal to n infimum capital T, and the previous lower bound, which here I obtained, which tells me how fast I'm going. And in fact, you can see that here the worst term is this one. It's n to the 3 a. You can see that a is q if you wish, but here it's the eighth moment. It's the eighth parallel of the q's moment, and beta, which you can match 1 if you wish. But I mean, you can have it in very general setting. Well, you know that this upper bound can be achieved because just of a kind of Markov's inequality, more or less. So you have some constant which depends upon terminal time, and here some negative power of n. And then you try to balance, and you see that provided that this coefficient is strictly positive, namely that alpha is less than 1/9, you're in business. You're in business because raising beta as much as you want, then you are going to be able to use the Borel-Cantelli lemma, and therefore you are going to be able to show that the series of these probabilities is converging, and therefore that almost surely your time Tn, where you are going above the threshold with the truncated equation, is going, the probability that this happens is going to be, I don't know how I formulated, but it's 0 or 1. Okay, and therefore, as usual, you can define your solution by claiming that on that set, on the set where Tn, capital Tn is equal to T, you said that your terminal solution is Un and everything is consistent. So you do get a solution, but a unique solution, but here there is a price to pay that our estimates more or less have this appear, and therefore we cannot go up to linear growth in this setting. All right, now we have well-posedness in LQ, and we would like to get more information about the solution. So the first more information we would like to get is some kind of Hölder regularity. So here it's very important that our domain be 0, 1, 0 pi to the power d, for d being 1 up to d, totem to 3, sorry. And now we have to have even a worse condition on our coefficient. And I should say that this section that I'm going to make a comment a bit further, this section is still in progress, because in a way, we are very frustrated that we cannot have at this step linear growth, because I'm going to comment similar equations which have, well, kind of similar equations which have been treated, for which people using a very nice techniques have been able to go up to linear growth in a fully nonlinear polynomial setting for the drift coefficient. But I mean, that's what we can do in this moment. So with this threshold on alpha, if you're 0 and continuous, we can show that U has almost surely continuous trajectories, and the idea is very simple-minded. We have several items in the right-hand side, and you look at the Hölder regularity of each piece. So, of course, the regularity of U0 can be handled in terms of, here it's very important to have an exact representation of the green function. Just upper estimates are not going to be good enough, so that's why we have to make this restriction on our domain. The deterministic part is dealt with using the very classical technique of factorization method. And the stochastic part is the nasty part, which imposes us to have more stronger coefficients on alpha. And here there is, okay, we also can get Hölder continuous trajectories for the solution, provided that our initial condition is Hölder continuous. And here I forgot to mention the fact that to get these results, we need that sigma be bounded. And again, because I'm not very happy with this section, I did not write them down exactly what the Hölder regularity are for that. They are connected with alpha. So once more, this is improving results which were obtained by Cardon-Weber in the case of stochastic Cahn-Hilliard equation. Again, on two hands. On one hand, we have the Allen-Cahn part, but again, it's not really a big deal. And on the other hand, we have been able to relax this boundless condition. So as I mentioned, there are several restrictions to our proof. So I think I more or less commented those. It is the part, the second part, which is really dealing with the stochastic integral, which is the most delicate to handle, while the other ones already it's very similar. For the other one, it's very similar to what Cardon-Weber did. Now, several works have been done in very similar setting for parabolic PDEs to try to go beyond, to get existence of and uniqueness for continuous processes at least, maybe not going to Hölder regularity. And let me mention some paper by Sandra Serra in 2003, and then a preprint by Kunze and Van Nerven from this year, where they have a completely different strategy. They do not use monotonicity. They do not use this green function approach. They kind of make a comparison between the more or less the same idea, namely to focus on the stochastic integral, to subtract it from the solution, to get a priori estimates, But then they are able to handle, because of dissipativity properties, they are able to use, let's say, energy inequalities in Banach spaces. So we tried to use this technique, and we could not. We could not, and maybe because we did not understand well enough their technique, but basically the reason, the deep reason I think why we could not do that is that we have the Laplace operator in front of our polynomial nonlinearity. And that means that I am not able to get just one Banach space in which everything would be fine. So if someone has ideas on how to deal in that case, I would be very, very happy to discuss with this person, because in this moment, for me, it's very frustrating. Okay. Now, okay, I guess I am going to be very fast, as usual. We'll have plenty of time for discussion. Let's move to regularity of the distribution. So maybe I'm going to slow down. So again, we want to deal with regularity of the solution for t and x being fixed. That means you have to make sense of the solution for fixed x and t. And therefore, we have to require that U0 is continuous. And that we are in this, with this hypothesis, that means that we have at least continuous, almost really continuous solutions. And now, the aim of the game is to prove that whenever t is strictly positive and you fix some element in your domain, which should be written script O, by the way, and not D, the distribution of U of x and t has a density.
So you don't need any estimate on the gradient of sigma?
Pardon me?
You don't need any estimate on the
no. We don't, no,
So you can
no, just a moment. Sigma is Lipschitz. Sigma is globally Lipschitz. So we do have a global estimate on the gradient of sigma. It's bounded. Okay.
But in dimension D, I mean, then it's just bounded, and this stochastic integral, which you write down sigma, well, you have the G then, one variable sigma times the dw. Is that working in 3 dimensions?
Yes, it's working just as well. This is not the problem. Okay, I'm trying to, okay. Let me just, okay, the problem is that, again, we have to take a threshold, because otherwise we have a problem. So we have to go back to, but again, the problem is not really sigma, because sigma is globally Lipschitz. That's the main point. So in a way, the answer to your question is yes, we have estimates on the gradient of sigma, it's bounded. And the problem is more here, this term, because this term has polynomial growth, and therefore it has no globally Lipschitz properties. And therefore, we have to cut off. Okay? So now we cut off with respect to, it's a different cutoff, it's kind of pointwise cutoff. So we look at the set omega n, where both, with respect to time and space, our solution is upper bounded by n in absolute value. And here we introduce this cutoff function here. So we have some new solution. And now the problem will be to prove that there is a Maljaver derivative for this solution, get an explicit formula, and get estimates for this Maljaver derivative. All right, so of course the first step is going to prove that this solution is differentiable in the sense of Maljaver calculus, and that it belongs to D1 too. And because sigma has, again, it's globally Lipschitz, we can do it. Now, on top of that, we have to get upper estimates on the derivatives. And for a while, we are going to suppose that sigma is 1. So the problem of boundless, I mentioned everything, is kind of irrelevant. So we have that uniformly with respect to time and space, our double integral of the square of the Maljaver derivative is going to be bounded by some constant which depends upon n, which is finite. And also, what's going to be very important is to put our hands on time integrals which are close to the end of the interval. Basically, because the formula which I did not write for the Maljaver derivative is going to involve the green kernel, and the green kernel becomes more and more degenerate as the time goes to 0. And therefore, the main part of the interval is not that which is close to 0, but it's that which is close to t. So then we can split So if sigma is 1, we can split the Mallier derivative in two parts. The first part, which normally should involve sigma times g, but sigma is 1, so it doesn't show up. And another part, which is going to involve double integrals. Now, as you might know, in order to prove existence of a Mallier derivative, you have to prove that something is non-degenerate, that something is strictly positive. And now what's important is to get lower estimates on that. And we have two terms. So one term, I1, which is hooked up in terms of the first term in our decomposition. And again, because the explicit formula of the green function we have, because we are in 0, 1 to the d, so we have a very explicit formula for our green kernel, we can get lower estimates in terms of powers of epsilon. And because d is going up to from 1 up to 3, this is a positive power epsilon. And on the other hand, we have I2, which is a similar guy, which is cooked up in terms of the second part, and which is going to involve those. So, roughly speaking, if we focus on this very tiny interval, the integral of this term is going to be much smaller than the interval of this term. That means that here we are going to have powers of epsilon, which are much larger than the one which shows up here. And therefore, the dominant term in this difference is this one, and we know how it behaves. Okay, so as I mentioned, sigma is the main term, and then you just compare the powers you get between the exponents you have here and the exponent you have in the second term, which should appear. And the comparison tells you that maybe I said it wrong a moment ago, because epsilon is very small. So the power which is in front of the main term is this one, and therefore you get something which is strictly positive almost surely, whatever n is. You don't care about n. What's important is that if you fix n, and if you choose epsilon of n small enough, you're in business. And now, suppose that sigma doesn't vanish, because that was my assumption to start with. Well, I'm going to more or less do the same, except that I'm going to have some factorization through sigma. And now Vn is not going exactly to be similar, but very similar indeed. Namely, it's going to start with G, which is the main point. So you make more or less the same decomposition. The remaining part for Vn more or less behaves as I claimed a moment ago, namely it has some G part plus some other part, and the very small integral, the time integral on the very small interval for the non-G part in V behaves exactly as before, and therefore again what we can prove is that for strictly positive T, this double integral is strictly positive almost surely, and once more the idea is here to shrink your time integral on an interval T minus epsilon n to T for epsilon n small enough matched to UN so that the remaining part, the most important part takes over. All right, once we have this almost sure strictly positivity, well, when we are in business, because we can use the Boole and Hirsch criterion, which tells us that whenever this occurs, there is a density of the distribution of our solution, UN, at time t and location x. We have absolutely no idea on the, well, okay, for u tilde n, we might be able to get our hands on regularity, on smoothness. But for the global solution, we cannot. And here, in fact, we just have these solutions, just this strict positivity almost surely is good enough in order to prove that the distribution has a density. And then let me remind you of what UN looked like. UN was a set where the supremum with respect to time and space of U was upper bounded by n, and almost surely, at least the probability that, I mean, omega n is of course an increasing set of subsets of omega, which goes to omega itself almost. So and therefore, and the way we have constructed our solution makes it that it agrees on U tilde n on omega n, and therefore we encounter at the very end that not only UN but U of T and X has a density. Just by this information we have about the probability that the two solutions would match. Okay, I guess I have been much too fast, and thank you for your attention.
So certainly we have, thank you very much, a lot of time for discussions and comments. So please.
Could you scroll back to the theorem?
Which one?
The equation. The first one.
LQ?
Yeah. So, but as soon as you know that U is in L infinity, almost surely.
We don't have moments.
Okay, but could you somehow afterwards use the factorization method again?
Oh, you mean to go to this function which I mentioned? The fact that I'd like to, as I told you, I mean, every idea will be welcome because in this moment I have the technique we are using is definitely not the appropriate one, that much I'm sure of. But I have no better idea in this moment. So.
But have you tried, for instance, in a fractional domain of the Laplacian to solve your equation?
What do you mean by that?
Oh, in a fractional Sobolev space instead of LQ.
No, I did not.
Because I think that would be the right thing to do.
That might be the trick to solve my case.
Because then you can treat the nonlinearity and you can use the factorization method afterwards or in between.
Okay.
I'm still a little bit puzzled about the final equation. If you have just the sigma of u and you have the sigma of u dw in a high space dimension, sigma of u is nothing better than Lipschitz.
Yes.
You have this kind of multiplication. Then how can this kind of thing be given a sense in this distribution? I mean, you see on the one hand side you have something which is a distribution, even pathwise is a distribution in some h minus whatever, h minus 4, right?
But I mean, it's continuous, so...
No. I mean, then you take the Laplacian on all of this.
Yes.
Yeah?
Oh,
So in space, I'm speaking only about space. And how is this product of the Lipschitz function with this dw, the white noise, without anything else?
maybe the answer to your question is this one. I'm writing at my solution in this form.
Yeah,
And therefore, I mean, all the gradients, there is no longer a gradient in front of you.
No, I'm even saying that you know that this gxt is whatever it is, right?
Mm-hmm.
So that's a nice smooth function, but I mean just the product of sigma and w.
Because I have to make sure that, I mean,
Because if
that's right, I have to make sure that this stochastic integral makes sense. But again, maybe I should have cut, yes, I guess I should have cut off my function, okay, you are right. I should have cut off inside of sigma as well.
And then the second question I have is, I mean, in analysis, usually we wouldn't take this function b, so we wouldn't take the fourth order operator, but we would like to write the whole equation in symmetric form, so we would take the first operator, so minus Laplacian plus identity, and its Green function.
Yes.
And then you have automatically this kind of gradient flow structure. Now, if you can make sense of the sigma w in a, let's say, in a nice negative space, the rest of the equation which you have there has to be just multiplied with mu.
Okay, but that might be a problem because I'm not sure that I can make sense of the sigma of the stochastic integral in a negative Sobolev space. I might, yes, I guess, I suppose.
And if you can make it with any C infinity function to start with.
Yes, maybe we can discuss and you can explain me a bit more. I would, as I said, any idea will be welcome.
Sorry. So I have started with my second question. Can you show me again the equation? What is your equation? Full equation.
This one?
This one. And what do you assume about f in your theorem 1?
It's a third degree polynomial with strictly positive leading coefficient.
It's a polynomial. Okay. Thank you. So more questions? Yes?
In your result on the existence of the probability density function, can you take several different space-time positions?
No, okay, this would be, of course, this would be a second step. In this moment, it's just at a fixed time. I guess we could take a vector at fixed time, which is more or less the same. But several times at small set issue, I didn't try at all. So I have no idea. I guess it could work, but I don't know. I didn't try.
And one other question is your Holder exponent in that theorem that you said you did not like so much, but was it sort of the optimal Holder exponent that you had?
I think for bounded sigma, yes, it is. For unbounded, I didn't mention it. So no, I think it's not optimal either. But as I told you, this whole section, in this moment, I don't like the way it looks. But I think, nevertheless, that if sigma is bounded, I would bet that it's the optimal. It's just because, okay, let me answer the following. If you think that the optimal Hölder exponent for the heat equation is strictly less than 1/2, and then this, okay, in dimension 1, it's strictly less than 1/2 and strictly less than 1/4, respectively, then it's just the same. So, and I think it is, I think these are optimal. I didn't try to get to prove that they're optimal, but I would be ready to bet that they are optimal. But for bounded sigma, for unbounded sigma, I don't.
Yes, one more question, please.
Maybe you say it, but I didn't understand well. So you have the existence of the density, but do you know something about the regularity?
No, I do not.
Where is the problem?
Non-linearity. Polynomial non-linearity.
And even, I mean, continuity of the density to see?
Might be, that I didn't try. But looking at moments of the inverse of the Malleable derivative and this kind of thing, that's hopeless. I think.
Oh, yes, ma'am.
So the green function depends on V, but it doesn't manifest on the conditions until V is 1, 2, or 3. So why is it so?
Just a very simple-minded answer. The basic step is that you want your stochastic integral to make sense. You square that, you want this to be infinite. And you see that it's not going to work except if d is strictly less than 4.
So I understand this, but when you have these conditions on Q and on alpha,
they do not show that. No, they are. That's right. They are unrelated with dimension. Yes. Yes. Maybe that's strange, but they are not related with dimension. But again, this alpha business is in progress. So, and maybe also I might mention that you can want to go in higher dimension, but then you have to get colored nodes. That is kind of easy to do.
I think we had a lot of discussion. So we still have 5 minutes break, and now let us thank Ali for this wonderful talk.